Imagine a time before time. There was no space, no matter, just a tiny point of unimaginable density and heat. We call this point a singularity. This is where our universe began. About 13.8 billion years ago. It's hard to grasp, but everything we see around us, every star, every galaxy, even ourselves, originated from this infinitesimal point. This wasn't an explosion in the traditional sense, like a firework going off in the night sky. Instead, picture the singularity as a rapidly inflating balloon. This is the Big Bang, the rapid expansion of space itself. It's still happening today. The universe is constantly growing, with galaxies moving apart like dots on an expanding balloon. The idea of the Big Bang might seem strange, but scientists have found evidence to support it. This evidence helps us understand the incredible journey our universe took from that tiny singularity to the vast cosmos we see today. Think about looking at a car speeding away from you. You'll notice the sound of its engine gets lower, a phenomenon we call a Doppler shift. Light waves behave similarly. When an object in space moves away from us, the light it emits stretches, shifting towards the red end of the spectrum. This is called redshift. Astronomers have observed that distant galaxies all show redshift. This means they are moving away from us. Even more fascinating, the farther a galaxy is, the faster it seems to be receding. This observation is a key piece of evidence supporting the Big Bang theory, suggesting the universe is indeed expanding. But there's more. Imagine the Big Bang as a fire that's slowly dying down. Even though the fire is gone, you can still feel its warmth. Similarly, the Big Bang left behind a faint afterglow, a whisper of its immense energy. We call this afterglow the cosmic microwave background radiation, or CMB. Think of the CMB as a baby picture of the universe. This faint radiation, detectable everywhere in space, provides a snapshot of what the universe looked like just 380,000 years after the Big Bang. Studying the CMB gives us valuable clues about the early universe, its composition, and how it evolved over time. The discovery of the CMB in the 1960s was a major victory for the Big Bang theory. It provided concrete evidence for a hot, dense, early universe, further solidifying the theory's acceptance among scientists. The Big Bang, redshift, and the CMB all point towards a universe that started from a single point and has been expanding ever since. But the story doesn't end there. Let's travel back to the earliest moments after the Big Bang to understand how our universe transformed from a sea of energy to the structured cosmos we see today. Section 4. From fire to atoms. The early universe takes shape. In the first fraction of a second after the Big Bang, the universe was an unimaginably hot and dense soup of energy. As the universe rapidly expanded, it began to cool. This cooling allowed energy to transform into matter, following Einstein's famous equation, E equals mc squared, which tells us that energy and matter are two sides of the same coin. As the universe cooled further, these fundamental particles combined to form protons and neutrons, the building blocks of atoms. But the universe was still too hot for atoms as we know them to exist. Electrons, the negatively charged particles that orbit the atom's nucleus, zipped around freely, constantly interacting with light and other particles. This era, lasting for about 380,000 years, is often referred to as the Dark Ages because atoms hadn't formed yet, and the universe was filled with a dense fog of particles. Light couldn't travel freely, it constantly scattered off the free electrons, making the universe opaque. Section 5. Cosmic inflation, a universe blown up. Imagine a balloon with dots scattered on its surface. As you inflate the balloon, the dots move apart, just like galaxies in our expanding universe. But this analogy doesn't quite capture the incredible speed at which the universe expanded in its earliest moments. This period of extremely rapid expansion, happening in the first fraction of a second after the Big Bang, is called cosmic inflation. During inflation, the universe expanded exponentially, growing from a size smaller than an atom to something closer to a grapefruit in an incredibly short amount of time. Cosmic inflation is crucial for explaining several observed features of the universe. It explains why the universe looks remarkably uniform on very large scales and why the cosmic microwave background has such a uniform temperature. Without inflation, these observations would be difficult to explain with the Big Bang theory alone. Section 6: Birth of our solar system, from nebula to sun. Fast forward billions of years after the Big Bang, the universe is now populated with vast clouds of gas and dust, remnants of the first generations of stars. One such cloud, called the solar nebula, would eventually give birth to our solar system. This swirling cloud of gas and dust, mostly hydrogen and helium left over from the Big Bang, along with heavier elements forged in the hearts of long-dead stars, began to collapse under its own gravity. This collapse might have been triggered by a nearby supernova explosion, a cataclysmic event that sent shockwaves through the nebula, causing it to contract. As the solar nebula collapsed, it started spinning faster and faster, like a figure skater pulling their arms in. This spinning motion caused the cloud to flatten into a rotating disk of material with a dense bulge at the center. This central bulge would eventually become our sun. Section 7: Shaping our solar system, planets from dust and gas. Within the swirling disk of gas and dust, tiny particles collided and stuck together, a process known as accretion. These clumps of matter gradually grew larger, forming planetesimals, the building blocks of planets. In the inner region of the disk, closer to the proto-sun, temperatures were scorching. Here, only rocky materials like iron and silicates could withstand the heat and condense into solid particles. These particles coalesced to form the terrestrial planets: Mercury, Venus, Earth, and Mars. Farther out, beyond a region called the frost line, temperatures were much colder. Here, lighter and more volatile elements like hydrogen, helium, and water ice could condense. This led to the formation of the gas giants, Jupiter and Saturn, massive planets primarily composed of hydrogen and helium. Even farther out, in the frigid reaches of the early solar system, ice giants like Uranus and Neptune formed, composed primarily of ices like water, ammonia, and methane. The formation of our solar system is a testament to the universe's remarkable ability to create complex structures from simple beginnings. From the ashes of dead stars, a new star was born, surrounded by a diverse array of planets, including our own Earth, a haven for life in the vastness of space.